Alright, and hello again. Let's see, let's get started again with a continuation of what we looked at in the previous video. Alright, so what I want to do is, for the second portion, is just run through a quick example problem of applying some of the principles of Reynolds transport theory. Alright, so let's work through this. Let me show you an example here. And the book has many more examples that you can look at, but I just wanted to give you a brief idea of how this is supposed to work. And we'll be working with this more in later weeks. So let me work through a quick example here. Man, I cannot write today. Example A. Okay, so let's say I'll start with my given, and I am given the following information. I'm told that water flows through a 2 meter wide rectangular channel. A rectangular channel with a velocity of 3 meters per second. Of 3 meters per second. So let me draw this. And I should say a uniform velocity. It has a uniform velocity of 3 meters per second. That will matter in certain cases. And so we're going to have a uniform velocity here. This is a channel. And it's going to be 2 meters wide, looking into the page here. And I'm told this information about the channel. And so I have a uniform velocity profile like this. Just a constant velocity profile all the way across the channel at each of the heights. Basically, this is an elevation view. Here, and the velocity, small v, equals 3 meters per second. And I'm going to say that I have control volume. I'll also illustrate that we have dimensions here. You know, since I'll use a different color for dimensions. I will also illustrate that I have dimensions here of 0.5 meters. So this channel is 3 meters deep into the page, or 2 meters deep or 2 meters wide, depending on your perspective, and it's about 0.5 meters tall. And I want to analyze a control volume ABC. So I'm going to have control volume. It's going to go like this. It's not going to be a simple rectangular control volume. It's going to be sort of a at an angle here. A trapezoid, I guess. And this is going to be A, B, C, and D. This is a straight line, in case you can't read my terrible drawings. And this is going to be, D here is going to be offset from C by a certain angle, theta. A certain angle, theta. And I want to find a few things. I'm going to have an A and a B here that I'm looking for. Find. Let's say A. Directly integrate. I want to directly integrate to find the mass flow rate. The mass flow rate across section CD. Across section CD. Across section CD of the control volume. Where B is simply equal to 1. lowercase b is equal to 1. And then b, I wish to do the same thing, but with b equal to 1 over rho. So my, in this case, my intensive property is just going to be that b is equal to 1, and here it's going to be that b is equal to 1 over rho, where rho, of course, is density. Where rho is density. All right, so now let's work through let's work through the solution. Let me make sure this is recording, etc., etc. And we are, so we're good. So let's work through the solution. And basically, I want to work through this via direct integration. So solution. Oh, and I want to directly integrate, this was also given, I want to directly integrate equation 4.16 in the book. I'm going to use equation 4.16 to find this. So the solution here, let's see, let's do A first, makes sense. A, well, we'll start with equation 4.16. And equation 4.16 says that B dot out of our control volume is equal to the integral of the control surface out B lowercase, I should actually say rho B, lowercase b, V dot normal vector n, and then dA. And we're going to use b is equal to 1, and I actually happen to know that v dot n is simply, in this case, going to be equal to v cosine theta. So in other words, if we have our if I have line CD here, if I look at line CD on the previous slide, what is n? Well, n is the normal vector of the surface. This is n, and this is the length of this thing has a length L. Again, this is C and this is D. And then the velocity, it has a certain, well, velocity is going at a different angle. This is our velocity vector here, and this is at a certain angle, theta. And from this is how I get v dot n equals v cosine theta. Okay, so therefore I can go and find, well, combining this together, I get that b dot out is equal to the surface integral of rho v cosine theta dA, rho v cosine theta dA. However, most of these terms are going to be constant, so I'm going to have rho v cosine theta simply times the integral of the surface integral dA. However, this is the area integral. This area, or this integral here, this is just going to be equal to the area between C and D. This is just equal to the area between C and D. And if I combine this together, I can find that B dot out is equal to rho v cosine theta ACD. Rho v cosine theta ACD. Let's see. So that's sort of our governing equation, rho v cosine theta area CD. Then, let's say I accept, let's see here. What can I, so that's one equation. I don't know, maybe I shouldn't have boxed that, but that's okay. Let's see what this does. First of all, I want to say area CD, let's actually try to work through this, is going to be equal to L times 2 meters. So at first it seems like there's a theta relationship, like the theta is going to be determining a contributing factor to how much mass is flowing past, or how much volume, mass, whatever, is flowing past the control volume at any given point. However, let's look at this. ACD equals L times 2 meters. But L is also going to depend on cosine. So we'd have 0.5 meters over cosine theta times 2 meters. So we're just replacing L with 0.5 over cosine theta. And this is then equal to 1 over cosine theta in units of meters squared. Thus, let's say we're using water with rho equal to 1,000 meters cube, or sorry, 1,000 kilograms per cubic meter, the density of water, and V equal 3 meters per second. Look what happens to my B dot out equation. B dot out is going to be equal to 1,000 kilograms per cubic meter times 3 meters per second times the cosine of theta times 1 over cosine theta meters squared. And if we look at this, well, let's look at the units. The meters cubed is in the denominator here, meters and meters squared in the numerator, so the meters go away. The cosine of theta here in the numerator will cancel out the cosine theta here in the denominator, and I simply get 3,000 kilograms per second for my B dot out. Interesting. 3,000 kilograms per second for our B dot out. 3,000 kilograms per second. Let's see. Let's make a note of something. Good. 3,000 kilograms per second. So notice, it turns out what's happened here is that this has become independent of theta. It doesn't matter what this angle is. The same amount of mass will be flowing past this boundary no matter what. And really this shouldn't be surprising. The channel is this boundary layer, this control surface. This boundary here is fixed. This side may deform depending on theta, but the amount of mass flowing past line AB is going to be constant. And so it shouldn't matter what I set this angle at. A control volume like this should have just as much matter flowing into it as flowing out of it. So every single kilogram of matter that's flowing into AB has to eventually flow out of line CD. No matter may flow out along AD or BC because those are the walls of the vessel. So we should not be surprised that we end up with a result that this is not actually dependent on theta. So let me save this here. And then let's work on part B. Let's work on part B. So then B, if I let lowercase b, our intensive property, be equal to 1 over rho, I will get that B dot out is equal to the integral across line CD of V cosine theta dA is equal to, and this will come to V cosine theta. So this is very similar. V cosine theta, surface integral integral CD dA, and this is just going to be equal to area CD. This is just equal to the area CD. And then this again is going to be equal to v cosine theta, ACD. Here, and let's see. Then b dot out, let's see how must I express this. Oh, and of course this area CD, as we found earlier, is also equal to 1 over cosine theta. So we'll need to use that again in this derivation, or in this part. So then b dot out equals, let's say 3 meters per second. 3 meters per second times the cosine of theta times 1 over cosine of theta. 1 over cosine of theta, 1 meters squared. And so we get 3 cubic meters per second, which is just our volumetric flow rate. So it depends on what property we're investigating. We can get different results. We can get different final outcomes. So we'll be measuring different things effectively. So again, final thing to note with all of these on this problem here, these are all independent of the theta. So do read the textbook, look through some of the examples there to learn more about this. We will be working through this more, especially when we talk about conservation of momentum, conservation of force, etc. But hopefully that serves as a useful brief introduction to Reynolds transport theorem and control volumes. So thank you. I will see you in class on Monday, and please see me if you have any questions. All right, thank you. Bye.